right, I'll give it maybe 1 more minute. Would that be okay with everyone?
Absolutely.
Okay, cool. Okay, I suppose I'll get started then. So yeah, thank you for inviting me to give this presentation. I apologize if any of you had attended my defense last week. Some of this will be pretty familiar, but I switched it up just a little bit to try and make it a little bit different and maybe better for discussion. And also, if any time throughout, if you want to hop in with questions, go for it. So this is work that was done with my advisor, Bart Nyssen, who I think is going to be here for the first couple of minutes and might chime in if he has anything to say. Basically, this work was done to try to kind of merge machine learning and process-based modeling. So the basic idea of what we did here was when we often sort of think about how we define hydrologic models, we would start with sort of a conceptual diagram and sort of draw out how all of the different processes are going to be either related or how they're going to be represented. And so the thing that that we decided to do here was put neural networks inside of the rest of the hydrologic model, specifically for modeling of transpiration and evaporation. And we're not actually modeling the water fluxes directly. We're using FluxNet data to actually have the machine learning portion simulate the turbulent heat fluxes. And then we'll let the rest of the hydrologic model transfer that into, or sort of use those heat fluxes as to calculate mass fluxes. And so this is kind of like the core idea, is just to use machine learning to represent individual processes in sort of a larger hydrologic model setting. So as I said, the training data for the machine learning and also the sort of what we're going to evaluate against is coming from FluxNet sites. We've got 60 different FluxNet sites in our study with over 500 site years of data. And this is all at the half-hourly time step. And then we've got just this map here shows all of the different sites, and you can see there's a decent mix of vegetation types, and the same for soil types. So it's a pretty diverse data set, and was pretty convenient because it also includes all of the meteorological forcing data that we need to run sort of the rest of the hydrologic model. So basically what we did then was we took a hydrologic model. We're going to use SUMA, which sort of is a hydrologic modeling framework that lets you choose different representations for individual processes. And so that made it kind of nice to incorporate these machine learning parameterizations, because it kind of was already sort of modular, made development a bit easier. So the sort of workflow of the model, you can say, is we've got parameters and meteorological forcing data as inputs, And then SUMA runs by computing all of the different flux terms, and then uses those to update state variables, such as the canopy temperature or storage, and soil temperatures and storages, snowpack states, things like that. And then once you calculate the updated states, they are used for the next time step to then further calculate new fluxes. And so I have highlighted here the turbulent heat fluxes because we're actually going to be representing them in different ways. So the first option that we're going to have is called SA, which we're calling SA for standalone. This is one of the representations of the turbulent heat fluxes that SUMA has kind of off the shelf. If you were to download and run SUMA, this is kind of what you would get. And so it takes in this calculation of these turbulent heat fluxes, takes in those some of those parameters, meteorological forcings, and then SUMA calculated states and fluxes. And it actually partitions the latent heat, which I have as LE here, and the sensible heat into different different domains. So here we have the canopy and the ground would be calculated separately. And then we have developed two machine learned representations of these latent heat fluxes. The first one we're calling NN1W for neural network one-way. And the reason that this is a one-way coupling is because it takes in parameters and meteorological forcings only. It doesn't use any of the other calculations that SUMA uses. And then it's actually just going to output the bulk latent and sensible heats. We're not going to partition it amongst the canopy and the ground. And this is mostly because the observations at FluxNet sites only give you the bulk heat fluxes. We think it would be cool for future work if you could actually partition these, but for now we just did the bulk. So basically the sum of the arrows in the essay. And then our other neural network parameterization is NN2W, which is a two-way coupling. In this case, we have the same sort of parameters and forcing data going into NN2W. And we also take in SUMA calculated states from the previous time step. So this kind of lets SUMA talk to the neural network as well as the neural network talk to SUMA. This also just outputs the bulk heat fluxes. And so just to highlight this a little bit more clearly, so you can kind of see how this works here. NN1W takes the forcing data and parameters as inputs, and then it outputs the turbulent heat fluxes. And then those are passed to SUMA for the rest of the calculations to update things like how much evaporation comes from the soil and to update those moisture contents. And then NN2W actually connects a second arrow back from SUMA to the neural network. And so we're inputting things into the neural network like the soil moisture and the soil temperature. And so kind of our idea here is can we get better simulations by coupling the two to talk to each other. And so just to kind of a couple other just methodological things here. SA was calibrated in sample. So we did a calibration at every single site, and then for part of the time series. And so this is an in-sample calibration. It's evaluated at the same place that it was calibrated. So we're taking this as sort of a benchmark, and we're hoping that the neural network versions can outperform it. And so both of the neural networks, NN1 and 2W, were actually trained out of sample in both time and space. So we did a 5-fold cross-validation here where we actually trained 5 neural networks for each of these configurations. So we trained it at 48 of the sites, and then the results I'll show are all applied to. So they're all, we train on 48 sites and then we apply it to 12 sites 5 times. So if you take those, if you take those 5 times 12, you get back to those 60 sites. So every time we evaluate the neural network, it's on data it's never seen, and for a site that it's never seen. So I'm just going to show a couple results here just to kind of convince you that it works. And then I'm actually going to show some stuff about some ongoing work that we're doing to try and understand this a little bit more. So sort of the baseline takeaway was both of these neural network parameterizations outperformed SA. So here on the 2 plots, I have the cumulative density functions of the KGE performance. So curves that fall further to the right on each of these plots indicate better performance. These curves are made up of each of those 60 sites. So there are 60 data points on these curves. So kind of for the latent heat, we see consistently that both NN1 and 2W fall about 0.2 kg to the right of the SA. And then similarly for the sensible heat, it's a little bit more than that. Just in general, NN1W and 2W kind of look like they're pretty comparable in performance here. So just at the 30-minute time scale, it seems that they're both kind of equivalent. You can kind of see in the latent heat that there's a little bit higher performance on average with NN2W. And so we looked at this over a bunch of different time scales, and I'm going to kind of omit that portion. But if you look at over the long time, over the entire simulation period, if you look at the ratio of the total evapotranspiration to the total precipitation, we can kind of get at whether or not the neural networks were able to model the long-term water balance well. And so in these plots, I have on the x-axis the ET over P from the FluxNet data, and then on the y-axis is the same ratio for the simulated. So in the left plot, we see for SA, and each of these dots is one of those 60 sites. So for SA, we see that we kind of have good performance when we fall close to the 1-to-1 line, and we tend to have under evaporation and more than over evaporation because most of the dots lie below the 1-to-1 line. And then the coloring is based on those cumulative density curves in the previous plot. But when we go to NN1W, we kind of see that the scatter is sort of symmetric. We have as much over evaporation as under evaporation. And so this is kind of because there's no information to the neural network to know when it should stop evaporating. Essentially, the neural networks only ever see one time step at a time. So there's no history or time dependence to it. So when it sees either high temperatures or high solar radiation, it's going to predict that it's going to evaporate, even if the soil sort of wouldn't evaporate as much. And so in NN2W, when we actually start including those soil states, we see that there's much less over evaporation happening. So this kind of indicates that the neural network can learn to detect these sort of thresholds. And it actually turns out that it learns really well to basically stop evaporating when the soil moisture is below the wilting point for the vegetation. So it actually does learn a pretty reasonable sort of cutoff. And this is actually what's kind of driving this long-term performance. This is where I'm going to stop with this work. And I'm actually going to start to show some stuff about new stuff that we've been looking at. So I guess before I do, are there any questions or discussion
for interrupting you. Yes,
oh,
I think you have a question in the chat box.
Oh, let me try and find that. Yeah.
I can read it for you. Jonathan is asking, is the site performance of SA and NN star correlated?
Sort of. On average, sort of yes. For the most part, the NN sort of configurations perform. Yeah, so I guess maybe if I go back a slide. So these are, each dot doesn't necessarily, if you draw like a horizontal bar across this, any sort of line across here doesn't necessarily represent the same site between the three curves. But on average, they do look sort of about 0.2 to 0.3 better for individual sites. There are probably about 10 sites where the NN configurations do worse. And this actually sort of appears to be at least some level an artifact of predicting the bulk heat fluxes, particularly during the winter. I think because it doesn't know or learn the vegetation cycle quite correctly, there are some cases where we get worse performance during winters. But yeah, overall, they tend to be correlated. Cool. And yeah, I guess I should also say one other thing while I'm before I go on. All of these model configurations actually do enforce mass and energy balance because they're running inside of SUMA. So when I say there's over evaporation, I mean compared to the observations, not that NN1W is predicting more evaporation than is possible. It's just more than is observed.
So Andrew, how do you enforce mass balance? Because your neural network is going to predict certain evaporation. So then you're balancing it out with what?
Basically, if the neural network predicts over evaporation, SUMA just says, no, you can't have that much. So it's sort of you can kind of think of it as a post hoc sort of enforcement of the network.
Basically, it's going to reduce the evaporation, or is it going to basically take it out of the soil moisture, or is it going to force back that into the soil? Where is the balance coming from? How is that balance? Because the number of pathways in which it has to be balanced is quite a few.
So when we take evaporation, we're taking it all as transpiration from the soil. Sort of, because we're predicting the bulk heat fluxes, it's a little bit simplified. So basically, we just say that we just limit the amount of prediction that the neural networks can actually output. We don't do any like compensating effects, if that makes sense.
Okay, maybe we revisit this. I'm still trying to understand.
So I guess,
but I mean, there is an error, right? And you have to back propagate the error somewhere to keep the balance. And if it's a multi-layer soil discretization, then you have to back propagate into those different soil layers. If it's multi-component evaporation and transpiration, you have to divide the error between those two and then back propagate. So I'm trying to understand how that mass balance is enforced. Maybe we can come back to later. I don't want to interrupt, but that's something I'm trying to understand.
Maybe to add a few. So in SUMA, the nice part is actually that the numerical solver is separate from the individual parameterizations of calculating the heat fluxes. And so SUMA actually, in its matrix solver, kind of enforces the energy and water balance. And so the new neural network basically provides a solution, and then it gets kind of iteratively solved the whole matrix. So there may be multiple passes through the neural network before we actually arrive at a solution that enforces the water and energy balance closure. As Andrew said, in this case, we're predicting only the bulk flux. So normally in SUMA, we would have the latent heat broken out into evaporation from interception storage, from ground directly, from the vegetation. Here we wanted to keep it a little simpler, so we only predicted a bulk flux, and so we have to determine where that water is going to be taken from. And so we actually take that out of the soil layers according to kind of the rooting profile of the vegetation in that particular element. So where the water comes from is actually a little different than if you look at the SUMA assay. It actually gets taken out of somewhat different soil layers. And actually, maybe Andrew, you can comment on that, because actually when you train the neural network, that was actually kind of an important part.
Yeah, right.
So hold on. So that's kind of how it's set up currently, and the reason it works fairly well is because SUMA kind of it doesn't do the evaluation kind of. It first calculates latent heat flux, and then it calculates the next flux and so on. They all get solved simultaneously as part of this matrix solver.
Right. I guess also one other thing that maybe is important is the neural networks were trained not actually in SUMA. They were trained outside of SUMA first. So basically, we did all of the training sort of off on its own, and then after training we put the neural networks inside of SUMA, where it runs in the kind of full mass and energy balance loop. And actually, in doing this, basically we kind of did like a laddered approach. So we calibrated SA, and we trained NN1W separately. And then when we trained NN2W, we need to include SUMA model outputs in the training data to incorporate those states. It turned out that the including soil moisture states or soil states from SA actually doesn't give you informative training data. So basically, when you train NN2W with states from SA, the sort of trajectories of the soil states are so different that it actually doesn't appear very useful. So what we actually did was we trained NN2W with states from NN1W's coupled simulations, and because because sort of the overall soil trajectories in time are more similar, or rather the heat fluxes that are predicted are more similar, this actually ends up being informative to the actual prediction of the heat fluxes using the state variables. So this is actually kind of in my mind an open question of what is the best way to do this, because I imagine we could then train a third neural network with NN2W states and get slightly different results, and hopefully eventually it would settle down, but it gets very computationally costly to train all of these networks. So that's a bit of a tangent, but I hope that kind of helps.
Yeah, it helps. I mean, still have some questions, but maybe we come at it during the discussion phase.
Sure, that sounds good.
Andrew, while you're here, sorry, that was my question too about the training that you just explained very well. I'm just wondering, just to add to that, if you could clarify. Of course, when you retrain your network from another initial random seed, you might get a wholly different neural network at the end. I just wondered if you looked at that kind of variability or robustness of your neural network in this context. For example, have you tried training multiple times inside and outside and see what would happen?
Yeah, so we kind of did this. So as I said, we did the 5-fold cross validation. So we actually end up with 5 trained model configurations for both NN1 and 2W. The stuff that I'm about to show, we started by actually looking at those 5 different configurations. We've since kind of moved past that. But just looking at the sort of what comes out of the training, looking at all of the weights and parameters of the network, they actually turn out surprisingly similar. Obviously, they're not exact, but they end up, if you kind of do some aggregation on the model weights, they actually end up looking pretty similar. And I think that this is probably why they were able to perform well out of sample, because I think it seems to be pretty robust, at least in terms of neural networks. Yeah, did that answer kind of? Okay, cool. Yeah, that's a good question. And I think you could also get at this a little bit if you ran them all and can start doing some uncertainty quantification on the networks as well, things like that. Okay, cool. I will go on then. So all of this work that I just showed kind of led to two main questions. The first is, did the neural network learn something physically plausible, or did it just maximize its or minimize some random sort of relationships? And then kind of the second question is, how did it learn to generalize between sites? Because we think that this is actually one of the things that's the most exciting, is this handled regionalization better than we were expecting it to. So to look at this, we're starting to use this technique called layer-wise relevance propagation. And so how this works is, so after you train these networks, you get a model that you can run in forward mode. You can provide inputs, run it through each of its individual layers, and do the computation to get some output. But the nice thing about neural networks is they're built for this back propagation of information. So when you train, you kind of update your weights in a backwards fashion. But this actually, you can take advantage of that sort of like computational infrastructure by actually propagating other things backwards through the network as well. So after we train the network, the idea of layer-wise relevance propagation is we're going to use some sort of a rule to try to assign how important an input variable was to make that particular prediction. So you can kind of think about this as like a local sensitivity analysis sort of idea, where for each prediction output, so at each half-hourly prediction, we can then run it in forward mode, get some output, but we can also take that output and then apply some sort of partitioning function to say this first node here was 2 times as important as this bottom node in the last layer. And you can keep doing that backwards and backwards and backwards until you get to your input layers. And that basically tells you input X was twice as important as input Y. So that's what we're doing to kind of try to figure out what the neural networks learned. And just really quickly, did that make sense? Because it gets a little bit fuzzy with, there's some arbitrary rule, which is it's just some mathematical function. It's not particularly important, but does this make sense? Okay, cool. So I'll just step through this for one site, this CH-Fru. It's a grassland site near the Swiss Alps. So we've got these 4 inputs that go into, we're training a new network and we're calling it NNLRP. It's almost the same as NN2W, it's just a bit simpler, which aids in the interpretation. Okay, so we take these 4 inputs here. They're kind of things that you can expect to be important for predicting these turbulent heat fluxes. We've got shortwave, radiation, temperature, relative humidity, and soil moisture. And the soil moisture is like a relative degree of saturation. So a 1 would be completely full and a 0 is at the wilting point. And so here we can make some predictions. And then LRP is not super performative. So you can see that we've got under prediction here, but it follows the seasonal cycles pretty well. And so that's more important than making super accurate predictions for now. This is sort of ongoing work. So we're kind of mostly interested in looking at what we can learn with LRP as a technique. So once we have these outputs, we can actually do that backwards propagation of relevance, and we get out individual time series. So one thing to note is each column is for an individual variable. So the bottom left plots are the relevance for shortwave radiation. And then the other things that you will note is the scale on these axes on the bottom are actually all different. And so the actual number of the relevance is how important it is, but we also wanted to show the variation in time. So the orange lines are for the relevance for sensible heat. And so you can see here, this orange line looks very well correlated with this red line in the bottom right panel. And similarly, the relevance to latent heat is the blue line in each of these plots. And in the case of shortwave, it's very well correlated to the upper right red line. So this is basically saying the neural network finds an almost one-to-one sort of mapping from shortwave to the heat fluxes, and then that's further modified with each of the other variables. So we'll see that temperature is actually more relevant than shortwave for latent heat, but less relevant for sensible heat. And these negative values are actually indicating that it's more of an inhibiting variable than it is a producing variable. So in this case, for temperature, we're seeing that that temperature tends to produce latent heat and inhibit sensible heat at this site. And so you can kind of think about when you have these sort of negatively correlated time series, you can kind of think of them as like a partitioning variable. So so the network is learning that temperature can be used to partition in some sense between latent and sensible heat. And then you'll note, so we have high degrees of saturation here throughout the year, and very low relevance to soil moisture. These numbers are much, much smaller than, say, shortwave and temperature. So if we look at a moisture limited site, this actually ends up flipping. So here I'm showing USWHS, which is in the Chihuahuan Desert. So it's an arid site. Again, we see sort of high levels of relevance for shortwave and temperature, but this time we actually see a much more sort of discernible signal for the relevance to moisture. And particularly, we can see that that the neural network kind of learns that evaporation should be active when we have sort of high levels of soil moisture at the site. So this actually, we can see that these are very, the two orange and blue lines in the relevance to moisture are very highly correlated. And so we can actually look at that correlation across sites. So here, I take the correlation between the blue and orange lines and then plot it against the aridity index here. So what we see is that sites that are left of this dotted line are sites where it's, you can think of them as being energy limited, and sites to the right of it are moisture limited. And so you can see that there's sort of this nice partitioning at that line. And so basically NNLRP learned to partition between the latent and sensible heat based on the aridity. This is interesting because the neural network has never seen PET or precip, and certainly not over a long time scale. It's only ever seen half-hourly data, and this is taken over the course of the entire simulation. So it's pretty interesting that it learns this partitioning so well. And it actually learns this partitioning in other ways as well. So we took the correlation between the soil moisture relevance and the relative humidity relevance to latent heat. And basically the soil moisture and relative humidity interact in different ways at the different sites. So basically when you have high relative humidity, you have high soil moisture relevance at arid sites. And so, so we think that might be the neural network learning that relative humidity is actually indicating that evaporation is happening, rather than sort of the other way around. And then you can also look at how the neural networks learn to partition the shortwave into the two latent and sensible heats. And again, we see this sort of partitioning happening. When it's very arid, the ratio tends to be low, meaning there's less relevance to shortwave just because it can't evaporate anymore. So these are sort of some of the things that we're seeing that the neural network learned. And we're looking at some other ways we can use this technique, but I'm going to stop there, and I think we should open this up for discussion. And basically just my takeaways are the coupling seemed to work pretty well. It allowed us to include those feedbacks. And then the LRP technique is actually seeming pretty promising for actually learning about what the networks are learning. And it seems that the networks actually are learning physically plausible things that we didn't give them information about. So yeah, I'll go ahead and stop sharing and bring it back for discussion. Yeah, thanks for listening.
So, yeah, Andrew, nice presentation. I'm trying to digest this. I mean, there are two perspectives. One is, I mean, you're saying, and I think consistent with some other research, that these neural networks somehow are able to predict better than physical process representation. And so they are able to incorporate certain elements of the processes, encapsulate them somewhere in the network in there, right? Mm-hmm. And the goal is then to see if we can uncover what additional thing they have learned that has made this higher prediction or better prediction possible. But what we have been able to uncover is just very broad categorization of water limited and energy limited environments, not the very specific, because our physical models will also respond in a similar way to water limited and energy limited. Model simulations will capture that, right? So I think what I interpret is we are not there yet in terms of getting the neural networks to tell us what more they have learned than is possible with the physical processes, but perhaps there is a pathway towards that, and in some near or further distant future. Is that how you're seeing it?
Yeah, I think that's pretty close to what I would say. I would say a couple, you know, I think there's some caveats to some of this. I think the two main ones are the neural networks we used here were they're just like the simplest. They're just feed forward. Every layer is connected to every other, or every node is connected to every other node in the next layer, which kind of allows the neural network to represent, like, it's got a lot of representational capacity. Like, it could learn a lot. And I think maybe constraining the network to be a little bit more tailored to the task would get us closer to interpretability. I also think the neural networks didn't have any constraints placed on them. That was all handled by the SUMA half. And so I think placing in some constraints can also make this a little bit more interpretable. And I think also the other thing I would say is in this case, we trained a network sort of to do the prediction. Now we're kind of asking sort of after the fact, like, what can we learn about it? I think there's probably ways that we can do experiments that are smarter. I think there's got to be ways to, like, design machine learning experiments that are actually sort of framed centrally for getting at asking specific questions about what can they learn. But I don't know. I don't have exact advice on how you do that. I don't know. Saman, do you have thoughts on this? Because your paper kind of touches on the ideas of, you know, what you can represent with a neural network. And
you know what? So we already know that neural networks are universal function approximators. So they can approximate anything, and that has been proven mathematically. So these are just hyper flexible tools, mapping tools that can relate anything to anything, even in the absence of any correlational relationship. So the caveat is, or so we should be cautious not to over interpret what we get when we get a neural network with, and you get a lot of neural network publications, not in hydrology, beyond reporting R-squared values of 0.99, which is interesting. And of course, in these studies, they always do some out of sample prediction, so-called validation, for example, and still they show good performance there as well. So something that I haven't been able to get my head around is that what they do a real or true out of sample prediction, a real extrapolation problem, or the data they use in their validation is just very similar to what they've been used in calibration. And so of course, in the type of analysis that we do in hydrology, it's hard to get our hand on some data that really haven't been seen in historical record. Of course, we chop our data period, but I mean, the change might not have been much in the past 30 years, for example. But if you think of some scenarios of warming, for example, what if your watershed warms up by 2 degrees Celsius? And that would be a real extrapolation problem. And I'm not sure exactly how the neural network model would work when it's not constrained by physics. And just to add to that, I think it depends on our philosophy of modeling. If our modeling objective or philosophy is only mapping, basically forecasting or prediction for short term, then perhaps what we get out of neural network is just fine, or even much better than physically based models. But if we see a model as a tool, for example, for diagnostic learning, basically to learn why something has happened and how it has happened in the past or currently. Of course, as you just very well explained, this is based on the connectionism notion, right? So you just stack many, now millions in the literature, of very simple algebraic operators that can be that are easy to explain at the individual level, but the collective behavior is not explainable at all. And you stack them all, and they can do everything for you. But you cannot, at the end, when you have a neural network model, you cannot isolate the different parts of the network and attribute. For example, okay, this bunch of neurons, for example, are responsible for evapotranspiration. This bunch is responsible for soil moisture. It's not like that. So they all work together to produce a response. And that makes it difficult for us to really get our head around, okay, what has happened, and learn the diagnostic learning, basically, philosophy. And similar in scenario analysis. So, for example, I live in Canada, Canadian context. We know that hydrologic processes are very sensitive to temperature. So because we always live around 0 degrees Celsius. And if you just change the temperature here just by less than a degree, there will be significant changes in hydrologic regime, because it will basically govern our precipitation regime, rainfall versus snowfall. Also we have soil freeze thaw. So basically all soil is frozen, no infiltration in winter time, and in summertime again filtration comes back, and snowmelt processes in general. And the system is just too sensitive to these kind of perturbations. So when we do scenario analysis in physically based models, we try to incorporate these things, these known physics, as much as we can. And of course, we know the range of validity of these known physics. And we know that we are going to stay, for example, in the range of validity when we do scenario analysis. But when it comes to neural network, I mean, it's not easy to constrain the behavior of the network to basically represent those possible changes. So if, for example, we raise the temperature by 2 degrees Celsius, then of course, we're going to get a wholly different snow melt regime or rain and snow type runoff and all those things. And you know what, when you haven't seen those in your pre-def record past 30 years, neural network technically has no way to extract any information, knowledge on it, because it is not available in your data. But we can basically implement our perceptions of what might happen in the future into the physically based model. So I think there is a gap still in somehow bridging this very powerful deep learning enterprise into hydrology. And you know, it can offer a lot of promises. Like you can easily handle big data with neural networks. You can easily scale it up and down with the amount of data available. But in physically based model, of course, it's not easy. But you know what? I think we are not there yet, and we're going to see a lot of interesting work, perhaps in the next 2 years, 5 years, and really bringing these two together.
Yeah, totally agree.
Andrew, I have a question.
Yeah, go for it.
Some of in your distribution plots of the performance of the neural networks, there's still some. You said there was about 10 sites that actually did worse with the neural network.
Yeah.
Then there's still some sites that are like performing fairly poorly, not compared to the physically based models. But how come the neural networks don't just perform well across the board?
Yeah, I
don't expect you to have an answer. I'm just
no, yeah, it's a good question though. I actually have two answers that cover maybe 20% of what we need to know, I think. The first one is data quality and just sort of unreducible biases of the observations. You know, some people will be pretty up in arms over that. I don't think it's, you know, long term a huge issue. I mean, it's unavoidable, no matter what type of modeling you're trying to do. And the other one I would say is human intervention is often not taken into account. So I know at least one of the sites that we kind of do tend to do poorly at or have some issues with is a site in the Netherlands. You know, there's no information at the FluxNet site, but it does appear that there is like pumping going on to maintain water levels or, you know, like the moisture levels. So that's like not incorporated anywhere. There's another site where I know that there's in like the sort of like FluxNet data annotation, they talk about like spraying pesticides and doing prescribed burns. And that's like, you know, like there's some of this you can find information about, but a lot of them, they're just like, here's the data. We're not going to tell you anything about it. Mm-hmm. So it's kind of, these things are happening, but we have no way to encode them currently. So I think that's another thing.
Do you think if those data were all like well understood and have all that information, that we could improve our process-based or physically based models as well to incorporate them?
Probably, I think so. Mm-hmm. I'm not saying it would be easy, but I think it's possible.
Mm-hmm. I just think it's really weird that there's a lot of, I mean, I think you're hitting on the kinds of things I was thinking too, but there's a lot of sites in streamflow prediction as well, where the neural network performs poorly on the sites that the process-based models are performing poorly. And I know that, I think that's really interesting right now. And particularly there's a stripe down the center of the United States where the machine learning models and the process models are all doing poorly. And so there's some sort of regional thing there. And it very well could be intervention through farming or something like that, because it's, you know, a high agriculture productivity area. But yeah, I think that's kind of interesting.
Yeah, definitely. And it's in some sense like the machine learning at least gives you like if it does poorly, it's, you know, in some sense because of the data.
Yeah, is that true? You think that's absolutely true?
Well, I think if you try really hard, you could all, you know, not never for the right reasons, but you could always get good improvement, or good predictions at a site. Probably not across multiple sites, but you know, if you can't across multiple sites, and there's one outlier that to me is sometimes, I don't know. I think there's some opportunity to use machine learning as sort of a data quality or anomaly detection thing.
Especially if we, you know, we hold it, like hold the idea that it can approximate any data transformation well, then if it can't do well in a lot of different sites, then there must be an issue with the data, I think. So it depends on how strongly you hold that assumption, but we certainly could, I think.
Well, I guess maybe there's two different things, right? There's an issue with the data in that there's bad quality issues in the measurements, but it could also be that there's just no predictability or no pattern in it naturally, right? So that might vary from place to place. But like there's basically other natural processes that we haven't got in the data set. So I wouldn't call that an issue with the data, but maybe more just incomplete. And maybe that also speaks to Saman's argument that you cannot predict out of sample or change in new situations. But I guess it's just about how much of the processes are in your data. So with this EA-LSTM models, you're kind of trading space for time, and you can maybe by learning across more different types of environments, you can also predict change better, right? So I think in the end, it's mostly about whether we have enough varied data to back up the complexity of the models and actually extract patterns from a big overview rather than zooming in on one particular area of the behavioral space. So yeah, I'm quite hopeful that in the next 5 or 10 years, you will see applications of neural networks that are more doing better for predicting really changing and non-stationary environments. But that's maybe just my optimism, or the salesman powers of the people writing about neural networks.
I just wanted to say something. It's a comment, or I just wonder what others think. So, of course, neural networks are not any new, and not any new to hydrologists. So the first surge of neural network applications in hydrology started back in early 1990s. And it lasted until mid 2000s. And of course, you might have heard of this AI winters. And that winter came to hydrology community as well. So we used to see a lot of neural network papers in hydrology. And that was about when I was doing my master's thesis in 2004. 2004. And then the field died. It didn't even look good to say someone, hey, I'm looking at neural networks. Oh, you're wasting your time. And because I did my master's thesis on a neural network, that was the kind of comments I was getting. Anyways, things now have revitalized. And of course, we see a lot of reinventing the wheels in some of the recent papers. And when you look back, a lot of these things have been done, even in hydrology community, but with a different group of people. Some of them have retired already and some not. And here's the point. Why did the field has been revitalized? What has changed in neural network capability over the last 20, 30 years? And I think this was my question. And the answer that I have in mind is that the computational power. So in methodologically, not much has changed. Of course, we have some better regularization algorithms and this and that, so better activation functions. But you know, these changes, these improvements are incremental, not a huge or breakthroughs. But what has changed is just the computational power, mostly the emergence of big data as well. Of course, in hydrology, most of the studies are not using the big data in real meaning. So of course, we have many more data, we have camel data set, but you know, they don't qualify as big data really, at least the way that computer scientists talk about. So then I think my word of caution is that we just have to be careful not to get overexcited and think through um, what could be done beyond what was done 20 years ago in our field, rather than just mapping. Of course, what Andrew is doing is one step forward, bringing neural network into SUMA. So these are emerging ideas. But anyways, yeah, and you know, a part of this overexcitement could be the boost by mega companies like Google, because of course, I mean, so in some other areas, there is a lot of potential. And you know, and you might have heard of even that Google is rolling out a machine learning based flood forecasting system. And it's now operational or something for Bangladesh. And I think they're planning to make it globally. And they're reporting R squared values of 0.99 or some, so exactly values that we haven't seen in hydrology really. So anyways, world is changing. Marketing is a big part of the business now, and we're scientists. So yeah, anyway, so that was a long argument or comment. I'm not sure about the exact point, but I wonder what others think in general about these prospects and excitements and sometimes overexcitements.
I think, like, you mentioned computational power as the main driver, but I think it really goes hand in hand with this better data sets that are more encompassing. So even maybe it's not big data in computer science terms, it's a lot bigger because you're adding this extra dimension of learning from many catchments at the same time and having remote sensing imagery and this kind of thing. I think that's a very significant increase in the type of data sets that we try to learn from. So I think that's probably as important as the computational power. And I guess you cannot do that without the computational power, right? So it's not just throwing more power at learning the same problem, but you can learn bigger problems with much more diverse data. So I think that's where the big leap forward is coming from, and I think it is the cause of maybe that winter is over for a bit.
Yeah. One other thing too, I think that's very true. But another thing is that the marketing of machine learning by the big companies like Google and everything like that, they, you know, I think most of us here are even a little too old to understand how much appreciation for machine learning there is. Like if you're an 18-year-old right now going into college, you've been hearing about machine learning for, you know, almost your entire life. And so, and you've not only been hearing about it, but you've been hearing about it's going to solve a lot of problems. So I think a lot of the people going into college and going into grad school right now, they're going to keep this interest going forward for a long time. So not saying there won't ever be another AI winter, but I think there's so many more people now interested in machine learning and AI than there was 5 years ago and 10 years ago. And they all have new ideas and new perspectives.
Did I miss the time on this meeting? Were we off by an hour?
Yes, I'm sorry. That
Okay.
happened. Hello, everyone. Again. We
So
are
you guys
glad
started.
to
You guys
join.
started an hour ago.
Yep.
Yes,
Okay.
we did.
Yeah, Arizona cheated on you, Hoshin. They don't go to a time shift.
This is going to be a problem for me because I teach until about 10:30 my time, so I won't be able to join unless we change the times.
We had to shift the time when we in fall, so maybe we need to revisit the time slot again due to that. So
Okay. So what was the question you guys were debating? I came in the tail end.
It was about where machine learning is going, and if it's going to continue, if the understanding of machine learning and process-based models is going to continue to develop over the next 10,
Okay.
5, I think 2 to 5 years was what was stated.
So I thought that was it, but I wanted to make sure. My view is that we tried to write a paper for US. They didn't accept it. Is that nothing has changed and everything has changed was the kind of the view on that comment. And when I say nothing has changed, what I mean is that science is still science. We use data, we come up with hypotheses, we test those hypotheses, and then we try to build our understanding. What has changed is that the tools that we use to do science and the amount of data that we have to do it has changed. So what you said, Jonathan, I think makes perfect sense. Students coming in, they're just going to go, oh, this is the new reality. We have a lot of, I mean, for them, it's not new, it's the reality. We have a lot of data and we have all these statistical tools, including machine learning tools, and we're going to use those to help us try to figure out what we're going to do. What I don't see necessarily is a shift towards just saying that prediction is everything, right? Because I don't think that that's what science was ultimately necessarily completely driven by. Stephen has a slight tweak on this perspective. Okay, if you go to the end, you might say prediction is everything, but along the way, I think what we're trying to do is say we need to understand the system in order to make better predictions. So the problem with, to me, the problem with machine learning is that you can only build relationships amongst observables. And you can do a really, really good job of that. But what about when you're trying to make predictions about something that is not observable?
But the same thing is true for any science, right? Well, anyone
Yeah.
can make predictions about non-observables, but predictions that get anywhere close to the truth need to have some kind of pulling back to the truth by some validation process. So
no, fair enough. So what do we do in science? We say that in order to make predictions about these observables, we have to speculate about the existence of certain non-observables. Right. That's the fundamental thing, these latent variables, these hidden things. Even machine learning does that by inventing the idea of latent variables, right? And then we have to decide whether those latent variables have any relationship to something that really exists in reality or not. And in science, what we do is we then say that we think these latent variables exist, and then we go out and design experiments to go and see if we can measure them. But in machine learning, we don't necessarily do that. We just say, as long as they give us the answer we want, we don't care whether they exist or not. To me, that's the overlap between physical science and machine learning.
So I just want to first say, kind of take it back a bit, but I think the other thing, and I think Hoshin basically said this, was the tools are now there. Like anyone can come in and pick up, open up the MATLAB, whatever, for neural networks, or in Python you can import torch.nn quite easily. So I think the tools are the third piece of it. Like we have the computing power, the software tools, and the data to make this all really easy. Like it's pretty easy to just run off a training of a neural network. But the other thing that I wanted to say was kind of bring it to Hoshin's last point, was like, what the difference between the two. And I think, to me, I see the future of these. I don't see machine learning as sort of a complete paradigm shift of science. I see it more of a new perspective on how to do optimization problems. And I think at the end of the day, to me, the really exciting thing that these machine learning tools offer is very well implemented and robust forms of like automatic differentiation. You could now write whatever, pick some hydrology model, your favorite one, whether it's something simple like HPV or something like SUMA. You can write the process equations in, say, an autodiff library, and then stick a neural network at the beginning or end of it, or as any other thing, and just train your entire calibration process through a machine learning sort of optimization routine. And I think that's kind of the exciting thing to me, is it offers a way to kind of wrap all of the pieces up nicely in one sort of framework.
So a couple of questions as a follow-on from that. One is, it's an old question, but I'm asking it again, which is, as the science progresses, the need for background training, educational, in some of these tools starts to come up, right? So our generation complains about the fact that students come in and they don't know how to program, and they don't have a good background in statistics, and they might not know algebra, and they might not know differential equations, or so on, right? And now we're adding another thing to that, which is you need to know machine learning, you need to know how all these packages work, right? So it's almost like we're saying you need to add another component to the educational piece, so that everybody has the ability to do all of this stuff. I had a second point, but I can't remember it now. It'll come back. What do you guys think about that? I mean, you guys are all having to learn it on your own, right? There's nobody teaching you this stuff.
Yeah, one thing is the way we learn it, or at least I do, is through YouTube videos and online tutorials. And that's the way a lot of kids learn most things now. And you can even tell the online videos, they have a particular style. They're aimed for people that watch online videos. And so I don't know, but I wonder if the learning for the next generation that pursues this stuff is going to be easier. But at the same time, it might not be as in depth, because going through a problem set in a textbook, for me at least, that's where I got most of my learning. The online videos is like how you kind of get to the point where you can start doing the problem sets. So
I didn't understand the problem set in the textbook. You're saying a book on machine learning which had problem sets that you could work through?
Yeah, watching a YouTube video gives me a baseline, so then I can start working through a problem set, and that's where my knowledge really takes off. So it's, yeah, I wonder how much learning newcomers are going to be able to do from videos.
So this is kind of why we have professors, right? Our job is kind of like to give you what we think is the bare minimum, right? Sort of the what that book on physics, there's a book on physics called The Bare Minimum or something that you
Six
need to
easy
know in order to
pieces.
be able to.
Oh yeah.
The theoretical minimum. Somebody wrote a book called The Theoretical Minimum. He was a famous scientist, physicist, in which he claimed that if you want to understand modern physics, this is what you need to understand, sort of about the background. I mean, it's sort of like if I want to use convolutional neural networks, what do I need to understand before I can even pick up any code, right?
But that's what
And
we
can
do.
I?
That's what we do with almost all the courses, right? I mean, we are providing the theoretical minimum so that there is sufficient training and background so people can pick up more advanced and not be surprised, saying, "What the heck is this?" But oh, this looks similar, familiar. Let me dive deeper into it, right?
You would hope. I'm not sure everybody's very successful at doing that, but you would think that a good teacher would be somebody who asks at least that question implicitly, right?
I'd also say there are certain aspects of it that we don't need to know anymore. I personally am happy that I am not, at least every day, deep in Fortran code, which requires its own special skill set compared to some of the higher level languages that are popular now.
And you don't need to know how to do numerical integration, right? Because the codes are all well established. But if you go back 40 years, a lot of us were immersed in day-to-day of, somebody was publishing a new way to do numerical integration that was more robust and stable than something else. So yeah, so hopefully some of that stuff goes away. Oh, I remember my second question. So what do you guys know about? So there's this move towards using rectified linear units, right? There's been a lot of talk about how using rectified linear units in artificial neural networks results in faster training than using sigmoids or other kind of units. But I'm also aware of the fact that if you initialize your weights incorrectly or badly, no learning will happen, right? Because it doesn't activate. Is anybody familiar with any work that's being done which says how to initialize your networks when you're using rectified linear units as the basic activation function?
I haven't worked with them myself, but I've read a little bit about this. They call it what? RLU, right? So you're right. So if you don't initialize it well, it might fall in your saturated zone, and that will never change in training, right? So to rectify that, they go with leaky RLUs. Basically, instead of having an absolute slope of 0, they just give it very marginal slope, so it remains active, but marginally compared to the rest of the network. So that is something
But has it solved the problem is my question.
I don't know, but I've seen it in the papers. I haven't used it. But but technically then you will, your activation function will never saturate, because wherever it goes, it still has some very small basically gradient, so it will change. And I have also a additional question on your question about these functions. So I've seen, for example, that they still call them universal function approximators, neural networks with these. So of course, with sigmoidal functions, it was clear, the proof, how it can approximate any function. But as soon as it becomes this form, I mean, I couldn't get my head around how it remains a universal form. I understand that in practice, empirically, you can approximate a lot of complex functions with that, but I'm not sure if it is truly a universal function approximator or not. I haven't seen the proof.
As far as I can tell, it is a universal approximator, and I think there is a paper somebody has published, but it's actually very easy to see by trying to make up a function with rectified linear unit, you could see you can basically pretty much make any function you want.
My
Sorry,
understanding
Andrew,
is also that the proof for ReLU's or rectified linear units are in the limit of infinite width. But to take it back to weight initialization, I would argue that, you know, as far as practitioners go, this is largely a solved problem. I personally actually used hyperbolic tangents because it captured high ends better, but I did train networks with the rectified linear units, and that, you know, you just use a weight initializer that someone at Google or Facebook has written, and it works fine. You don't need to think about it anymore. You know, if
So
you're
somebody
really
has
in the
already
nitty
figured-
gritty, then sure you might. But, you know, for you know, the audience of this, it feels like you just go with one of their initializers and it's good to go.
Okay.
You know, I was talking to someone from Facebook who does deep learning for natural language processing, and I asked, okay, because if you look at their models have millions of weights, and even they published a paper recently with 1 trillion weights. So I think it's super huge neural network for natural language processing. And my take of his response was that, you know what, they just go very large because they think they have the computational power, or of course tons of data in the web, and perhaps they're not like us. They don't discuss really model complexity versus information, all those things. What is the trade-off? They just go with the most complex one that they can. And of course, when you have such a big network, then many neurons might just be inactive. I don't know, but you know, they just look at the result rather than under the hood, what's going on really in their very complex network.
So they don't necessarily prune out all the inactive, they just leave them there. But
I
if you
think
were,
they might some, but yeah.
Interesting.
And you know, there was a talk, let me tell you this, a couple of years ago that I watched just recently. They have a conference called NIPSO or something like that. And there was an award talk for an hour. And that talk was very interesting in a sense that a prominent AI person, I would say, someone from Google, received this award and said, hey, what we do is alchemy. And he basically said the same thing. He said, we go with a very complex thing and we can never explain what's happening. And of course, we get a result. But the problem is when that model is used to support high-stake decisions, that would be a big problem. And you know, he gave an interesting example. He said, I flew to here and I was on an airplane. I wasn't worried that I was on an airplane because I knew that some scientists, engineers knew exactly how that airplane works. They designed all the pieces, everything was clear. But he said, you know, for neural networks, even me, I can never explain what's happening in my giant neural network. So that was a word of caution. And you know, that created a lot of controversy. There is now, then there is some follow-up pieces on that. For example, another prominent computer scientist basically attacked this guy, say, hey, no, this is not the case, and some others support it. So there is some nice debate in computer science community on this as well.
Well, doesn't this have to do with the whole issue of fault tolerance, Saman? In that, for example, when you're building a very complex piece of code, Microsoft is building a complex piece of code, and it's still got bugs in it, right? There's some random occurrence of something that happens, and your code crashes, right? And this used to be a common thing for us, where we'd get the spinning wheel or the spinning hourglass, and we go, oh shit, you know, my code's crashing. I've lost all the work I did for the last hour. I'm not talking about code. I'm talking about Microsoft Word or one of these programs, right? So what you're saying is something analogous to, if I don't know what's under the hood, then I don't know when it's going to crash, right? But the counter argument has been that neural networks are very fault tolerant. So I'm curious, you know, in other words, because they have so many pathways and circuits that even if something crashes, something else compensates for it.
Yeah, it might be the case, but I think the problem that they were talking about is that you never know if the prediction is truly accurate. And another example I saw was that they were using somewhere an AI system to support the judge decision to keep a person in prison or not. And that was a very high stake decision. And there was an article on it that now an AI is telling, and we need to know exactly why AI is telling us this person should be kept in prison. This is a very high stake decision. And yeah, I mean, that lack of explainability sometimes is the problem. I know it perhaps goes back to our mathematicity thing from George Box years ago. And there is a very interesting statement also in a paper that I read again recently by Hornberger and Spear back in 70s, saying, and computational models of back then, they said clearly that we can as the modeler or researcher, we can design the modeler to produce anything we want, or to generate any response that we want. And I mean, these are scary things that so needs to be vetted and needs to be clear for others
But
really to review. And
but aren't you talking about an issue of ethics, right? So I'm reminded of the Italian scientists who they tried to take to court. I don't remember exactly what happened because of this earthquake situation, right? And a similar problem is Google, with the self-driving cars, where the question is, who's responsible if the car kills somebody, right? So you're getting into this issue of, if you don't know what's happening and why it's happening, how do you assign responsibility?
yeah,
In the case of the Italian scientists, it wasn't anything to do with machine learning. It was still saying, you should have been able to tell us this and you didn't, and therefore you're liable. It's kind of a complicated thing. It had nothing to do with machine learning. Sorry, Jonathan.
Yeah, I wonder if that question is so relevant because the machine learning is advancing so quickly. Like the airplane analogy, the people working on the airplane now probably don't understand airplanes as well as they did in the 1930s, but they don't need to because there's tools that automate things. They're designing parts in AutoCAD rather by hand. And but that's kind of okay because there is an incremental progress in airplane development that the knowledge that was needed at the time was passed on to the next person working on the advancement. But at this particular time, we might be allowing people to make an advancement without the sufficient knowledge to make sure their incremental advancement is robust.
So this has to do with faith in the system, right? We allow National Weather Service to make flood forecasts because we have some level of faith that they have tried and tested their algorithms and vetted them and so on. And we use ModFlow for legal cases, even though it may not be the state of the art in terms of groundwater modeling, because it's been tried and tested and vetted. So how do we do that when we're doing this?
Well, one thing we do is we're constantly benchmarking against known solutions.
Right.
And benchmarking against the models that have gone through that vetting process.
Did you guys get that request survey for about reproducibility in hydrological science? Yes, there was a survey sent out by a bunch of people, including Thorsten Wagner and so on. Because there's a big debate in many of the areas about the fact that when we submit our papers, our results are not necessarily reproducible. Right, and so journals are now probably need probably know something. The journals are now requiring people to provide their code and their data sets. But just because they provide their code and their data sets doesn't mean that their results have actually been reproduced.
That's the responsibility of the people who want to reproduce. So,
but I mean, we're ending up trusting the results coming out of paper because it sounds right rather than,
yeah,
and we're trusting that the people who did the paper did everything correctly and reported honestly what they did. Yeah.
at the end of the day, I think the responsibility rests with the author, right? I mean, it's not the reviewer's responsibility to examine everything. They can only go so far. Particularly, I think it's easier to examine the theoretical side, but not so easy to examine the computational pieces in there. But I mean, it's the author's responsibility and reputation. I mean, there's code that we put out 5-6 years ago with my former student, Fong Lee. And there are some people who asked questions just last month saying, hey, we're not unable to run the code and so forth. So we helped them out, or Fong Lee did, saying, okay, this is how you run this thing. So people are trying it out. I mean, so I think that's the right way to go. I still have some concerns regarding that. I mean, with a lot of the things that we are doing, we are making everything open source, but at some point we have to consider that as intellectual property as well, right? So what prevents a company downloading this thing from GitHub and using that to profit from it? And there's no way for you to find out whether they're using your code, because then it's protected under their intellectual property. So you have to actually file a lawsuit and to go through all that process, but you don't know what's happening in there, right? So there is this scientific progress where you actually have to make those things available, but then there's a whole intellectual property question that has not been well addressed. And it is an intellectual property, much like you create a piece of hardware which you can protect, but a lot more time and effort also goes into software. So there's a whole suite of those issues then.
So what I'm hearing is that science proceeds by consensus, which is pretty much what we were all taught, right? But what if this company uses your code and gets sued? Can they turn around and sue you because you have the intellectual property rights on that piece of code?
Well, most of the licenses you put on GitHub, for instance, specifically say that you can use the code, but you can't trust it. Like the MIT license.
Yeah, we basically say that this code is openly available for research purposes, all right? But nothing stops anybody from adopting and making money. If they don't get sued and they make a ton of money, I mean, we never know, right? In there. So I think that there needs to be an effective debate regarding that. I mean, we want the science to actually have an impact in society and make a difference. So if it is, I mean, that's satisfying. But I mean, the students or anybody else who worked on it are probably not benefiting, and somebody who didn't contribute. MATLAB is the biggest example of this. I mean, they employ a ton of people whose job essentially is to sift through published article and implement emergent numerical algorithms. And then they are licensing it to the universities all over the place. All right. I mean, you have to pay for it. And so, I mean, they are not creating.
So it's user beware.
But in a way, like they're licensing it because they add value, because anyone can still take that code as well, right? So it's not that they're taking the code away from other people to use. So I think there's nothing wrong with. I guess you can specify it in your license what you allow and what not, right? But indeed, you're right that it might be hard to enforce that.
Well, yeah, I think I was saying is, I mean, they're even taking a lot of theoretical developments and translating it into code. And the people who are developing the theoretical providing the theoretical constructs, it's an intellectual property, right? But they are not benefiting from its translation into code, and MATLAB essentially benefiting from that as a private company. And there's a whole series of debate we can have that happens with all the publishers as well. I mean, I thought the publishing model is probably the biggest gimmick on earth, right? Hoshin, you remember we had this conversation when we were with WRR. It's perfect. A journal basically draws upon people who have found money from elsewhere. It draws upon people who are reviewing it, and basically it draws upon people who are publishing, and you have to pay for it being published, right? So essentially, journal is providing absolutely no value to to the process and still profiting. And if you look at all the private corporation like Elsevier and all, these are like tens of billions of dollars every year, right?
Well,
So,
well, they're providing the organizational structure, arguably, right?
yeah, but
Yeah.
archive provides that. Put it in there, you're done. I mean, essentially, no review. Authors are responsible for the content, and
Sure.
anybody who's using it has to double check and verify. So the responsibility is on them to make sure
Well,
that
what they're saying is we're selling credibility, right?
yeah.
Journal is selling credibility, and if you can't get it published, somehow your work is not credible. And the rest of us buy into that myth. And as long as we buy into that myth, they have power, right?
Yeah.
The same is true in almost every business in
Yeah.
the Western society.
Yeah, the other gripe I have about is with all the people who are doing software development. So if you wanted to go and practice civil engineering, you have to have a license, basically saying you're qualified, you have a certain amount of qualification to certify a particular design or so forth that is being implemented because it impacts human beings and lives and all that stuff, right? But software engineers require absolutely no licensing. A high school student could be writing a code that goes into a plane navigation system. I mean, there is absolutely no checks and balances, and if it crashes, who's responsible, right? So that's an extreme example, but nevertheless, there is a whole suite of different places. So should there be licensing of these kinds, or what is the mechanism for doing this? So we haven't had that kind of a debate in there. And as software gets more and more pervasive, going back to machine learning and stuff like that, I mean, these things are going to pretty much drive a lot of the onboard decision making, right? I mean, self-driving cars, planes, or you have it. And somebody has to take the responsibility that the people who are actually writing the code know what it is doing. Right? If you don't know the math, you don't know the things, how do you guarantee that? Who's responsible for it?
So are we losing the ability to have consensus? Because arguably, when we wrote the code for shuffle complex evolution, for example, the reason it got used a lot is because people tried it and tested and said, okay, it works and we like it. It's not because we said it works, because other people tried it and tested it and it works, right? So that's the consensus mechanism of science operating. And then when something else worked better, they stopped using this and they started using something else. So how does that apply to the machine learning models?
I mean, one thing that I'm starting to wonder is like that I see all these curves for performance metrics for machine learning models across a large array of sites, 100 sites, 1,000 sites, and there's a frequency curve of, but I always see there's a tail where some sites are getting poor results and then some sites are getting good results. And the goal seems to be in a lot of these papers recently is just to move that cumulative distribution function a little further to the right. But what isn't clear is which one of those is improving in which basin. Not every basin is going to be improved by the new machine learning algorithm. So if you are moving an average curve to the right, you're not necessarily and then you apply it to a particular basin, you're not necessarily, how do we know we're using the right machine learning curve? So I think that is a big problem, because we can't just say, oh, this one performs better on average, so we're going to use it. And then, let's say you're the, Oklahoma City flood control district, and you're going to use the best performing deep learning model for your flood forecast. But it turns out that the one that actually works best for your site was, 3 years ago in a very simple model or something like that. So
one of the things Luis was doing in his work was he was looking at the CDF curves, but he was looking at the CDF curves of the increments. In other words, point by point, you measure the difference in performance, and then you plot the CDF curve of that. And that's the curve you want to move to the right, not the location agnostic curve, but the location specific curve. And yes, you do see performance getting worse.
yeah. I guess it would come down to, the person who's going to use it for an application needs to have some sort of understanding, not just take a model and use it. And that's always been the problem in hydrology, probably for a long time, is someone just takes the model and starts using it without understanding what's in it. And that was true for physics models as well. If somebody takes a two-dimensional hydraulics model and does a dam breach study, they don't really understand how the St. Venant equations are being solved in that particular model. I don't know if it's any worse.
This boils down to what I've always said, is we need a science of evaluation, which tells us how do you actually evaluate things in different circumstances. And that's back to education, the component we're talking about. For example, you have situations where you're trying to detect a positive like cancer, and there's, let's say, only 2% of people in the population who actually get something. And just by the way you report the statistics, you can make your thing sound really good, because it's reporting all the successes at predicting no cancer, but its success at predicting cancer is actually worse than guessing. But the statistics that you report can make it sound like you're doing a really, really good job, because it's not measuring the thing that you really want, that you really care about.
Yeah.
The false positives and whatever, the contingency table stuff. Yeah.
Mm-hmm.
And
That was a proposal.
I just wanted to say, I've looked a little bit at the literature on flood forecasting in Canada by neural networks. And, in 2000s-ish, there were some people in Canada, in Ontario in particular, publishing a lot of papers on neural network AI for flood forecasting. And neural network looks a great tool in that context, because it's real-time or short-term forecasting. Neural network is good in mapping, and typically it can do better than other type of models when you look at the metrics. And also it's very good in a data simulation context, because at each time step you can quickly retrain or whatever neural network and improve your prediction. But they couldn't convince any of the water authorities to use these systems in practice. And that is interesting. Perhaps in Canada, the only place that they have a neural network-based flood forecasting system is somewhere in Vancouver Island that I've read about, and that's related to Environment Canada as well. And I've been talking to some flood forecasters. In Canada, of course, perhaps unlike US, flood forecasting is very fragmented. Each province has their own team. In my chat with them, perhaps they don't know exactly what's going on in some of the physically based models that they use, but they are more confident, because they have to make high-stake decisions in Alberta. For example, if people evacuate these areas, they're not comfortable on basing their decisions on a neural network type model that might show superior performance in the hindcast, but they have no confidence in their future prediction. But an HPV type model, even a simple model, could be very informative for them.
But don't you think, Saman, that this is history repeating itself? Okay, so go back to 1980, and Suresh comes along and he says, we've got a way to calibrate your models using automated optimization, and you got to use the right objective function, which accounts for heteroscedasticity, and we can show you the results are better, and the National Weather Service doesn't want to use it, right?
Yeah.
And that's mainly, but my take on it is it's because the people who have to make the decisions are relying on their comfort zone, what they know, what works, so on. And anything that's new, even if it's demonstrated to be good, is not necessarily going to replace their sense of comfort. Right. So are we at the same stage where we're saying that we can show that machine learning models make better predictions, but people will stay with the physically based models just because they know them, they're comfortable with them, they know how to use them. And it's like in civil engineering, when I did my internship, if you were to design piles, these vertical things, you could only use certain diameters because everybody had only used those diameters. So if your math told you that a 12.5-foot pile was the optimal pile, they would say, well, but we've only ever used 10-foot and 15-foot, so we're going to use a 15-foot diameter pile, right? You're basically hedging your bets because you're saying, I'm not going to do something new or different.
Yeah,
because in the past.
That could be partly it, but the other part is SCE still is explainable, and someone who does manual calibration can get their head around, okay, now let's do it automatic. But moving from a physically based to a black box type paradigm is a big shift. And you know what? So neural network has been around as long as SCE has been around, right? Earlier first, and neural your own work is back in.
But my point is that the Weather Service changed its attitudes about forecasting when the old people retired and new people came in. Right. So what happens when the new people coming in are trained in machine learning? They're going to have a completely different comfort zone with machine learning, and that happens on the time scale of 10 to 20 years. Right?
Yeah, I think that's a possibility.
On the other hand, they're under pressure because if somebody comes in from outside and says, yeah, but I can really show that I can do better than what you're doing, how much can you hold back and say, no, I'm not going to use the best available technology just because I don't like it? What are you seeing in Canada? Is you saying there's a strong resistance, and it's mainly because
in general, I wouldn't say strong resistance because I haven't done a survey really, but just based on personal conversations with people in Canada, hydrology community hasn't been much welcoming these new techniques, and at least people around me. I don't know exactly, but so there are people who do neural network type stuff, AI stuff in hydrology, but typically they work in isolation. They don't merge well with the rest of hydrology in Canada.
my hope is that we will see a hybridization, right? That somehow we will preserve some sense of physical intuition while incorporating tools that give us better process representations, better so on and so forth, so that we don't actually lose that sense of comfort.
I gave an informal proposal to GWF, for example, to add a dimension to global water futures around machine learning data science, and it was turned down. You know, I mean, so there are some old school thoughts in Canada. I mean, I'm not saying it can be generalized to Canada, but it's definitely Canada is not there yet.
Okay.
I guess my feeling is it's not necessarily a bad thing that society tends to be slightly conservative. So
let's try to make them ready, someone.
Sorry?
Let's try to make Canada ready for it.
Yeah.
Right, exactly.
Yeah, yeah, you and I should work on it. Yeah, I mean, so you need funding basically, right? So
yeah,
to make something.
So do you have to go through GWF for all your funding?
Not necessarily, but you know what? I thought, you know, GWF had plenty of funding, and say, yeah, you know what? So why not? And you know, so some of the prominent AI scientists are from Canada, right? This legendary Jeffrey Hinton, for example, is Canadian. The other guy from Montreal, I didn't know them. Hoshin pointed me to them at first time. So it's, I mean, Canada is doing well in terms of AI in other disciplines, but in hydrology, no.
Before we go, guys, Stephen, have you seen this book?
By Hutter? Is that?
Yeah.
Yeah.
I'm hoping to read it this summer, but it's completely based on Solomonov probability and Kolmogorov complexity.
Yeah.
As the basis for, so I thought you'd be interested.
Yeah, I've seen it. Like I think Shane Legg is the former PhD student of Marcus Hutter that wrote his thesis on this.
Okay.
And he's with Google DeepMind now, I think, or with DeepMind. So yeah,
Marcus Hutter moved to Australia, I think.
Yeah. So he's fully into this Solomonov induction, and then adds basically reinforcement learning to it. So the best decision theory with best learning theory, and that's like theoretically the best intelligent being that kind of maximizes any objective function in an unknown environment.
Well, I'd like to keep the conversation going on this complexity control issue, because it sounds, you know, like people are making progress on figuring out how to actually implement it in a practical sense.
Yeah.
Sorry, can I ask what the publication year is on that book?
Yes.
Because I've just spent some time reading the 2011 paper that has the same title.
Yeah, the book is 2005, so it's probably a bit outdated in some sense.
Okay.
But I'm hoping it at least gives the basics so you can understand what they're doing. There's a bunch of YouTube videos, if you just Google Marcus Hutter, where he talks about these things.
Over the holidays, I got into that, and I really loved it. And this 2011 paper, A Philosophical Treatise of Universal Induction, I really liked that.
Yes.
That was fantastic. And then that led me to, Stephen and I were talking about some recent work from Max Tegmark using symbolic regression, which I think is an implementation of this.
Yeah, that's actually like it's called AI Feynman.
Oh, AI Feynman, yeah.
Yeah. And like you can read in the paper, they use this complexity penalization as well, and it looks very similar to. I guess then was it true that they kind of made some simplification to it, like I guess they counted the number of
Operations. Yeah.
operations and the number of integers that they used.
Yeah, so they reformulate the expression in reverse Polish notation and use that length as the complexity of the expression. So they I think the really clever part is in how they narrow down the search space, because I think a part of it is just, here are the operators, and so based on the number of operators, that's the complexity of the search space is just coming up with some way to combine the operators and the number of parameters, and so that gets enormously complex really quickly. So they had a really clever way to narrow that down. But yeah, the complexity at the end was just they reformulate the expression in reverse Polish notation.
Dan, is this something you'd be willing to present to us at some point, since you've done already some reading on it?
Yeah, maybe. Yeah. Yeah, I just kind of played around with it because what you can get the AI Feynman library, and that was just really fun. Stephen had an idea. Well, why don't we just look at the really cool thing is, they basically discover this set of 100 equations, right? Kind of fundamental physics equations. Some famous set from Richard Feynman lectures. And so I thought, okay, well, what if we just look at, we use a standard power equation for a stage discharge relationship, right? So I just took, I don't know what, 30 or something, 30 stage discharge measurements and plugged it in, and it came out with this Pareto optimal front of all these different very simple relationships that I guess it came out with something that resembled, I don't know, Stephen, do you remember? It came out with like a double exponential, which apparently was the most concise, but also had the best accuracy. And when I then translate the standard stage discharge equation to to get the same complexity, to be able to plot it in the same field, that equation is dominated. So,
and I think maybe that had something to do with the parameters for the power law. I think it's either you use an integer of a certain complexity, or it's directly like a double or a single precision float or something. But there was nothing in between. So I would say you could kind of reduce the complexity a bit by rounding off these non-integer exponents and save a few bits, right?
yeah.
Anyway,
Yeah,
it would be nice to revisit that topic. In particular, I'm curious because the move in machine learning is towards saying we're not going to care about parsimony at all. We're just going to use these basic rectified linear units or something, and we can construct any function of any arbitrary degree of accuracy by combining many of these, right? But I could imagine a future in which we use complexity control to replace these functions with effectively equivalent operations which don't have the same number of parameters, and you might want some of these tools to be able to do that. Right?
Yeah, I think, Stephen, what you were just mentioning about the precision, because I noticed that they have, by default, they have I think a precision that's something like 6 standard deviations. It's equivalent to something like that, like very, very high precision. And so you have to go in and actually, I kind of like pulled it out and made it into a parameter, because, what we discussed, like the precision of our data was very low, but they were setting a standard of like, I think they put it in terms of powers of 2, right? So they put 2 to the minus 30. That's the precision they were specifying in this.
So that's the difference between the exact science and the inexact science, right?
So I changed it to 2 to the minus 6, and it's still like a, you know, that's a really interesting part of it that I'd like to dig more into. But it's still kind of like, you know, plotting this the stage discharge equation that, you know, it's like good luck going to anybody and saying, oh, you know what, that's, you know, that equation. There's this other. There's something simpler that we should be using. Like that's so deeply ingrained. But then all these other equations, you know, basically dominated that equation. So I mean, obviously this was just like I just spent, you know, a couple days playing around with it, and it requires a lot more thought. But yeah.
Yeah, I think.
So you came up with a representation of a stage discharge curve which was simpler than the classical ones. Is that what you just said?
Yeah. So have you seen the paper that accompanies AI Feynman?
It's been a while, so I don't remember. Yeah.
Okay. Yeah. So the output is, you know, it's a what is it? It's complexity. It's a plot, right? So it shows a Pareto optimal curve, and on the x-axis is complexity, and the y-axis is its accuracy, some metric of accuracy. And so, you know, it finds a whole bunch of, I guess, feasible solutions, and it plots them, and it plots the Pareto optimal front. And then, you know, so they use what do they use the example of, like I don't know, like gravitation or something like that, Gm small m over r squared or whatever, and it's this really nice, you know, kink in the Pareto optimal front where the, you know, there is a more accurate equation that it came up with, but it's much more complex. So yeah, I really like that. It was a really intuitive way to describe that. Yes, there are, like, you know, equifinality is the real thing, and really there is no such thing as, I don't know, maybe I'm wrong in this, but maybe there is no such thing as a, like, fundamentally correct equation for describing something. It's just whatever you have that suits your needs, and so I really like
within
that.
a certain level of accuracy. Yeah.
Yeah. And so the simplest one is the best one. Yeah.
So that feeds back again to the machine learning things, which is you could be pushing the envelope on the decimal points, but maybe you're just adding too much complexity compared to the accuracy you're gaining. That's why I like the complexity control argument.
Yeah, so in machine learning, it's kind of done by empirically by doing this cross-validation and stuff, right? So you're constantly trying to test out of sample, and that controls complexity, while these methods would control complexity beforehand without separating the data. And maybe that has the, so in machine learning, you can control complexity by just setting these huge matrices of parameters to set most of them close to 0, but not exactly to 0. And with this approach, you're kind of forcing the complexity or the simplicity to be more visible in a way. And maybe that helps understandability as well then.
Well, I can imagine that. So you could always make the argument that you're going to have robots, but the intelligence is going to reside in the cloud somewhere, right? And so you can have a very, very, very complex representation, but at some point it becomes inefficient, right? And you want the intelligence to reside on an individual robot mind, and which means you have to have complexity control, because you can't rely on one massive intelligence. You need little distributed intelligences which can function in an environment. So
yeah,
I can't imagine this thing going in one direction only.
Yeah, that's interesting.
Okay, better go.
Okay.
This is
Yeah.
very interesting. Thanks, guys.
Thanks,
Thank you
Leila.
everyone for the discussion
Yeah,
today.
Dan, if you don't mind, it would be really nice to hear about that sometimes. So I'll let you work that out with Leila when it works with your schedule.
Okay. Yeah,
Great.
sounds good. I'll have to
Yeah, it sounds good.
maybe dig in a little further. Thanks.
All right. Thanks, guys.
Thank you everyone.
Bye.
Yeah.
Bye.
Bye.
Leila,
Bye.
you'll be sending out the link for this, right? So I can go back and listen to the talk, the Zoom.
Yes,
Yeah.
absolutely.
All right. Thank you.
Yes.
Bye.
Okay.
Bye.
Bye.
Bye.